Good afternoon or good morning, depending upon where you are. This is Steve Case with Electrorent, and welcome to our webinar, Navigating Complexity in Optical Networking Challenges and Solutions for Coherent Optics. We have two great speakers with us this morning, and from Quantify Photonics and Lumentum, and so we'll get started. Sung-Hoon has 15 years of experience in Coherent's the telecommunications industry and involved in planning, design, and sales of communication test products at Quantify Photonics. He'll be our first speaker. Our second speaker is Mark Stiller, and he's a VP of Transmission Product Line Management at Lumentum, makers of those products, and is a veteran in the telecommunication industry. I think we're all here now. Good morning, guys.
Good morning.
Good morning.
Okay, before we get started with the talk, just a brief introduction about Electrorent and how we play with this. Electrorent is a large test equipment company, of course, representing a lot of different OEMs in the industry. We've got 1.1 or $1.2 billion of assets all around the world. So no matter where you are, we can probably provide you with the type of test equipment that you want. We have offices and warehouses in the US, of course, the UK, Malaysia, China, and other parts of the world as well. So if you do need help in a place, even if it's overseas, we can usually get equipment to you. So that would be one of the things that that we can definitely do for you. Another thing I did want to mention, and I know I'm mentioning it first, guys, but we are going to be at OFC, and of course, Quantify Photonics is going to be there, and Lumentum, Quantify Photonics in booth 1331, and this is coming up starting March 26th at OFC in San Diego. And of course, Lumentum is going to be there as well, and booth 2613, and Lumentum is in booth 1331. Okay, and with that, I think we're just going to go ahead and start with Sung-Hoon Im. I'm going to let you get ready there and make you the presenter.
All right, thank you, Steve. Hello, everybody. This is Sung-Hoon Im from Quantify Photonics. This morning, I'd like to start this webinar with a quick recap on what coherent communication is. So comparing it to a non-coherent communication, also often called intensity modulated direct detect, IMDD, coherent communication utilizes the phase of the waveform to modulate data. And by doing so, it's giving you more number of bits per each symbol transmitted. So as you can see from this diagram, intensity modulation only encodes the data on the amplitude or intensity of the light. And to measure that signal, it's relatively simple. You put it through to the oscilloscope and you get an eye diagram. For coherent communication, you use modulation formats such as QPSK or QAM. In the case of QAM, you are modulating not only the phase, but intensity as well. So you plot your signal on an IQ plot, and there's an example on the bottom right corner. And as you can see here, as in the case of 16 QAM, you're getting 16 individual and unique states from one symbol transmission. So the benefits of coherent communications include you can achieve higher data rates. You are encoding more bits per symbol transmitted, and you can transmit longer distances. Now, coherent communications use DSP or digital signal processing, and it's capable of compensating for impairments such as the chromatic dispersion. And since you are transmitting more bits within the same bandwidth of the signal, you are achieving a higher spectral efficiency. And again, thanks to DSP, you are able to compensate and correct for many of the impairments in the fiber links and transmission hardware. So you are effectively achieving an enhanced signal-to-noise ratio. So if you look at what is involved in measuring such a coherent signal, here is an introduction to an OMA, or optical modulation analyzer. This is the kind of instrument you would find in an R&D lab measuring coherently modulated signals. So firstly, you have your coherent receiver. This is where mixing of the signal light with the unmodulated reference light happens. The optical coherent receiver converts optical signal to 4 RF tributaries: X polarization I, X polarization Q, Y pole I, Y pole Q, which are then passed on to the real-time oscilloscope for data acquisition. I've displayed 3 vendors of oscilloscopes here to help aid understanding here. So you have high bandwidth, high performance real-time scopes from Tektronix, Keysight, and Teledyne LaCroix. Now that's not it. So once the oscilloscope acquires the raw waveforms, the DSP has to be performed before a meaningful information can be received or deduced from the raw data signal. So the DSP, or digital signal processing, performs calibrations and corrections. It compensates for various things. It realigns the polarization, and then it provides that decoded information in a form that us humans can understand, such as visual diagrams and numerical parameters. So again, to emphasize on the role of the digital signal processing, here is a slide that kind of demonstrates what happens along the DSP chain. So you get your raw data from the oscilloscope coming in from the left. You perform hardware calibration to correct for any impairments on non-ideal performances, such as the frequency response of the hardware, any skew that may be present between the 4 channels, etc., etc. Now, you can compensate for chromatic dispersion if you've gone through a long length of fiber, but you'll notice that at that point, the constellation diagram is still a mush. It doesn't provide any meaningful information there. Now, once you decouple the 2 polarizations, X and Y polarization, you start to see something that resembles a ring, and it's still a ring, or the constellation is still rotating because there is still the frequency offset from the 2 lasers that's been mixed. Once you've removed that frequency offset, the rotation stops, but you'll notice that the constellation still has that radial smudging, and this is due to the phase noise of the laser. But the good thing is the DSP is more than capable of compensating and removing that phase noise as well. So once you perform phase estimation, you end up with a nice, stable, beautiful constellation diagram that you can tell the quality of. So performing this DSP is a crucial part of an OMA system. Let's have a look at the OMA solution that's been available in the past and currently. So there has been a solution that pairs with Tektronix oscilloscope, one with LaCroix oscilloscope, and a Keysight oscilloscope. And until now, each vendor of the oscilloscope kind of tied the coherent receiver and the OMA software to only work with that particular oscilloscope brand. So the solution has more or less been exclusively packaged up as their own system, and there has not been a flexibility on what kind of software you can use together with the oscilloscope or receiver hardware. So it really came down to the preference of the real-time oscilloscope, your choice of your OMA system. Now we're introducing a brand new OMA software. We call it VISIC. This is set to change the whole game. Now this is a third-party software that's designed to work with all kinds of real-time oscilloscopes and providing you that tool, the analysis, the DSP that you need for the OMA measurement. So you can utilize the existing real-time oscilloscope that you have in your lab, and it's going to be an incremental addition to enable you the ability to measure coherently modulated signals. So a coherent receiver hardware, we manufacture coherent receivers also, by the way. So you're able to add on the receiver and the software to your existing real-time oscilloscope to reduce on the initial investment and get the ability to measure coherently modulated signals. In addition to working with all three vendors of oscilloscope, the VISIC software also is set to change how users use it. It's designed to be interactive and intuitive, and it's very modern and to overcome some of the pain points that have been with the legacy OMA softwares from the three vendors. The legacy software, here's one example. They tend to be designed for users who's quite familiar with the coherent DSP and knowledgeable about algorithms. So it lacks transparency into what happens or what goes on behind the scenes. And it allows you to select and use the algorithms, but it doesn't really intuitively explain, what happens in what order, and you're not able to fully reconfigure the DSP itself. So in our modern approach to the optical modulation analysis, here's a summary of the new VISIC software. It's software oscilloscope agnostic. It works with all three vendors. It's, again, built from ground up to be intuitive. So I'll demonstrate this to you after the slides, and you'll start to feel how intuitive the software is. And it makes the DSP simple and easy to understand. So we've included the latest and the greatest automated algorithms so that any optimization you need is done automatically to save you time and make sure any measurement you make is optimized at all times automatically. And we display the DSP in what we call the sequential pipeline. And this form of displaying the DSP is very transparent. You know exactly what is happening behind the scenes, in which order, what functionality is being performed. And in addition to that, we give you on-the-fly reconfiguration ability. So you can change parameters while looking at your signal, and immediately in the next scan, you see the impact of your change. So when you're trying to adjust or optimize, it really provides you a very quick time-saving way to, say, optimize your system. Again, being a new software, it gets the benefits of a modern interface. It's touchscreen friendly. You control by dragging and dropping, and it's remote control compliant through Skippy and gRPC. All right, so let's pull up the live software that's running on my laptop now. So here is VISIC. So on the left, you see the DSP pipeline that I mentioned earlier. So it tells you from the top down what is happening in the DSP. So you have the coherent receiver calibration. So you import your calibration file, and this usually is the factory calibration file you get with the coherent receiver. And then this happens. So this is the fine tuning of any residual imperfections, and this happens automatically on the fly. So currently the values are static, but if I was to reset this, you'll see the constellation going bad and iteratively improving and optimizing itself. So the algorithm is figuring out what the skew, any residual skew or gain imbalance or offset present in the receiver hardware from the signal measurement. And of course, you can put it to continuously train so that you're updating this all the time. But unless you're changing something with the hardware, these values are pretty static. So we usually train it for say 20 acquisitions and let it stay with that. So as you can see, yeah, automated optimization all the time, and you are making reliable, repeatable measurement every time. It reduces human error. It reduces chance of some hardware parameter changing, the skew changing, and getting a different result today compared to yesterday. All those are gone. The software takes care of it for you. You retime. Okay, so following the DSP pipeline again, you resample from this node, and notice how each node or box is labeled with its functionality. So it's really easy to understand what happens. This is the polarization demultiplexer, an equalizer, really easy to follow. If you want to add more functionality by clicking on Add Nodes, it opens up a panel with available boxes that you can drag and drop. So if I was to stabilize it, any offset in the IQ, I can drag this along and place it there, and it'll have an impact. And you can also bring in your own MATLAB algorithm, and you can place it anywhere you want. And you can import your code here. So this really makes it a customizable tool that you can use even to verify your algorithm or try out different filters or something. You really can customize a DSP if you want to. Now, you can add and remove, but you can also rearrange. And a good demonstration here is to see if I remove, say, carrier offset removal node, what happens to the signal? You immediately see, oh, by removing that offset removal, now the constellation is spinning because there's a beat frequency or frequency difference between the two lasers. Now let me add that back in. Carrier offset removal, yeah. And also similarly, adding in the phase, removing the phase estimator should show you what that does. Okay. Now, if I remove the phase estimator, you'll start to see it's not a full rotation, but it's kind of unstable rotationally, and that's due to the phase noise of the laser. So it's a great educational tool as well. You get to learn about what each individual functional nodes do, and yeah, you can get a hands-on experience, and it's a great tool for learning about the coherent DSP. All right, let's put that back in. So Yes, that's the DSP part. It presents the data in numerous visualizations. You can turn on more graphs like point carrier sphere for your state of polarization. You can also turn on optical spectrum, total frequency graphs, something like that. So you can customize how you lay out the graphs and also the measurements. There are many more measurements available for you to select and populate the table here. And it's all about user friendliness. We even have added the signal summary bar down below that shows you the information that you've told the software. For example, if you go to signal summary, you've told the software it's 16 QAM, the baud rate, the carrier frequency, so that whenever you make a screen capture to document this data, you have these data on that screenshot, so it helps you with documenting. It's really user friendly. And again, you're able to save the raw data, a train of raw data to playback, and that's what I am doing currently. So this is, I'm running it from a saved data file that has 10 sets of measurements in it, and I'm looping through that. And as you've seen, this is the raw data, so any DSP I change or modify gets freshly applied to it, as if you are working with real data from the oscilloscope. Yeah, so the brand new software, intuitive, user-friendly, unmatched flexibility. This is changing the game by giving you the ability to choose and match the parts of the OMA system, and even let you utilize the existing inventory of real-time oscilloscope that you have already in your lab. So if you're interested in learning more about VISIC, please get in touch, and after a little questionnaires, we'll set you up with a trial version. Thank you, Steve. Back to you.
Yeah, thanks, Sung-Hoon. Actually, I did want to mention, and we're getting a couple of questions asked, that we do have a Q&A panel in the GoToWebinar application here for you. And so if you do have some questions, go ahead and ask, and we're going to have a roundup at the end of the webinar, and we'll get to all the questions. But thank you. We already have some questions, so that those are all good. And right now we're going to switch over to Mark from Lumentum and see if he's ready for his part of the presentation.
Okay, let's see if I can figure this out again.
You are not. Oh, there we go.
All right. Well, thank you, Sung-Hoon. That was really cool. I really wish that you had come out with this 10 years ago. It would have made life so much simpler. What I'd like to do is step back and look from a kind of end user perspective, and as a supplier of modules, our perspective on where technology is going. Because I think the kind of capability that we just looked at becomes increasingly critical as the complexity and the speeds on coherent optics continue to be driven forward. Okay? So, real quickly, Lumentum provides components, modules, subsystems, and chips, optical chips, into a wide variety of networks. If you can imagine everything from your handset to the submarine cables that span the world, everything has something inside from Lumentum. So rather than try and tackle the entire universe of optics, we'll focus today on the coherent module space and where it's evolving to. So we have kind of a maybe complicated view of how networks are evolving. In the end, what drives this is the cost per gigabit second over distance. It has the capability of driving bandwidth over a number of different application spaces. The technology that's been driving this on a continuous downward slope has been the CMOS process node for the digital signal processing chips, right? Everything Sung-Hoon showed in the test equipment then has to evolve into a CMOS digital signal processor and optics set that can be mass produced. Okay? So CMOS, when Coherent first started, 40 nanometers. Today's volume shipping is at 6 and 7 nanometers and moving rapidly to 4 and 5 nanometers with the next node. And what that does is it reduces power. It also allows the ability to do more complex signal processing. Okay. The second is the increase in baud rate and modulation density. Again, Sung-Hoon, thank you for the nice graphic showing the constellations. I think it's a critical point that Coherent introduces phase as a second coding level. Call it PAM 4x4, where you introduce phase as well as signal levels. So the evolution from 100 to 200 gigabit per second at the same baud rate, then you double the baud rate, double the baud rate, double the baud rate to continue to pack more and more data into a single transceiver. Okay. And of course, as these evolve over time, the test equipment also has to evolve to adopt to the higher baud rates and the different constellations and coding types that get used as we continue to drive in this direction. One thing that has changed is this evolution path after 400 gig no longer gives a higher bandwidth per fiber, because now the baud rate is beginning to, the channel count decreases as we continue to fill the spectrum. Okay, so our view is this will continue up to 1.6 terabits per second, 256 gigabaud, 16 QAM. There will be the introduction of other technologies in coding to help improve the efficiency and lower power consumption. But fundamentally, we think this is about where this path runs out, as a combination of the technology, but also the investment cost to continue to drive each generation of signal processing chips. Okay, so the question is, what comes next? And that's what we call the 6th generation. Okay. Right now, we're using single carriers. What we see coming next is what is called carrier division multiplexing, where you now fit 2, 4, 6, 8 carriers within a single signal spectrum. Okay. You wouldn't think this does much, but actually by using the subcarriers, you can also use some RF techniques to fit more and more signal within an existing bandwidth. And this is something that's already been pioneered by a company called Infinera, but we see this becoming, in one way or another, much more broadly adopted. The other, it's a fancy word, spatial division multiplexing, use more fiber. Okay. It's very expensive to install fiber anywhere. So over the last, probably 10 years, every fiber that's been installed is actually a fiber bundle, and the size of those fiber bundles has grown. So some of the hyperscalers, their data center infrastructure has a minimum of 3,000 fibers per run. Submarine cables are rapidly increasing, and actually there's a lot of clever techniques that allow you to fit more and more fiber in a smaller area. And then finally, most of Coherent is being done in the C-band. L-band is now becoming table stakes. O-band, S-band, E-band are all on the table over the long term to continue to fit additional density in. So the picture is basically a continuous evolution of bandwidth. There will be some limitations on baud rate, but we still have a ways to go on that. And then additional techniques coming in to increase the amount of capacity. Just a quick snapshot. Right now, today, We have products running at 200 gigabaud that are going into the market. So 64 is volume production, 96 is volume production, 130 is the generation just starting deployment now, and 200 gigabaud will be deployed end of this year, early next year. So this is moving very, very quickly. Okay. As you can see, the electro-optic characteristics are incredibly critical here, but it isn't just the Mach-Zehnder that is a fundamental piece of the modulator. It's also the entire RF signal chain, balancing the DACs and ADCs and the DSP, balancing the TIA and its gain characteristics, and the driver and its gain characteristics. So again, going back to the Quantify presentation, I think the ability to put in MATLAB models, not just for the DSP, but for the whole signal chain, it's an incredibly powerful capability. Because this becomes more and more difficult as time goes on, and I'm not showing the phase maps, which is even more complicated. Another way of looking at this is the evolution of form factor and the network level support. So traditionally, networks have been built with transponders. Transponders contain telemetry, fault detection, predictive analytics. They contain diagnostics that monitor the link and monitor themselves. And then the layer 1 and layer 2, the data encoding. Okay, not just the phase and amplitude encoding, but also the transcoding and standards-based code framing requirements that allow the equipment that all of the optics plug into to be able to consistently interpret and decode the meanings. Okay. So, transceivers have traditionally been very simple. They're just optics. But in order to use them, they have some of the layer 2 framing and coding capabilities. And we're seeing more and more diagnostics to where today transceivers look a little bit like a piece of test equipment, to be honest, right? Because of some of the diagnostic capability, the self-compensation capabilities that are embedded in the digital signal processor. And if you take a look at where things are today, this is a nice chart that Signal AI, updates. I really like it. If you take a look at the evolution by color code of the different generations of transceivers, it's really about speed and distance, right? So for short distance, 60 gigabaud, for low speed, 60 gigabaud is fine. But if you want to go up to 1.2 terabits, you need 120 gigabaud and beyond. These have traditionally been system level demonstrations, and what we're seeing now is the new generation of products that runs at 60, 80, and 120 gigabaud is now starting to show up on this chart as being capable of system level performance. Okay. So, when we look at product development and we look at how to optimize, the test equipment solutions are a really critical piece of this. We rely on companies like Quantify to be able to tell us the pure quality of our transmitter, the pure quality of our receiver, and then we know what the best we can do is, and can take that and try and implement our closest approach in volume production. And then this is just an example. This is a QSFP-DD, which is a very small form factor transceiver. It plugs directly into a switch or router like Arista, Cisco, Juniper, Nokia make. This is the newest generation, and it's capable of plugging onto an existing network and transmitting up to 2,000 kilometers of data. This is something that only 4 or 6 years ago would have been 10 times the size, 10 times the power, and probably 10 times the cost. Okay. So this is the generation that's up and coming. It's higher baud rate, different module, different constellation types. We're also starting to see the onset of probabilistic constellation shaping, which is changing the amount of energy in different points of the constellation, right? Because the outer points suffer from a larger distortion. So you're no longer looking at linear constellations. Another thing that is both a limiting and enabling factor, the transition to smaller form factor also means that these get plugged into much smaller pieces of equipment, and cooling becomes a real issue. Right? So, both in network, in the testing equipment that we use, but also in the actual field application, there are limitations for what's possible. But again, as a look forward, the existing switches and routers deployed in networks today, we're able to carry up to 90 gigabaud. There are both standardized FECs, right? The forward error correction and proprietary FECs. There is signal shaping, Nyquist shaping, or the making of the changing of the signal spectrum to be squarer. The probabilistic constellation shaping won't be supported here, but in the next generation routers, which are just coming into the market, higher baud rate, multiple FECs, signal shaping, probabilistic constellation shaping, and then the expectation of much longer dispersion reaches. Okay. And then finally, there's transceiver type, larger transceiver types that are more traditional to the telecom equipment racks that are running up to 140 gigabaud and beyond, and have even stronger shaping, PCS, and other capabilities. One thing that underlies all of this and is critical to the market is the ability to interoperate, to have the same product perform on multiple host platforms, and also interoperate with other modules. And in order to do that, there needs to be standardization around every element. This layer 1 being the optical layer, layer 2 being the framing and coding. These are embedded in standards that are now called CMIS and CCMIS. This is a management interface standard that is now in the OIF forum. And there's looks going forward at a next generation interface that contains an even richer diagnostic set. And again, the comment back to to quantifying the test equipment. This will never be as good as the test equipment needs to be in order to develop a truly effective and accurate set of diagnostics. And so we really do rely on some of the advances like Quantify is making. And again, the flexibility and openness of that platform is really important. And the technology itself is sometimes advancing ahead of standards. The traditional standards have, I don't know how many generations, maybe 10, 15 generations of Ethernet, standards that all need to maintain compatibility forwards and backwards. So a set of MSAs and forums have been developed to bridge those gaps, and they push the boundaries faster than the standards bodies can. But overall, I think the whole community has done a good job on doing standardization so that we can have an interoperable and open network. Okay. So that's it. Thank you.
Thank you, Mark. That was actually excellent. So now we have our chance here to ask some questions. So I'd remind everyone that if you'd like to go ahead and put the questions into the questions part of the webinar. And we do have a question. I think maybe it could be for either, but Sung-Hoon, I think maybe it's for you. For the VISIC software, is the VISIC approach based on standards from ITU, IEC, et cetera? Does it implement forward error correction as a part of the process, or FEC?
Right, good question. So VISIC software, it measures physical layer signal itself. So what you see, the constellation eye diagram, is before you take into account the encoding. So the FEC and things like that come later. If you want to make, say, BER measurement, you need to then consider, is there FEC or framing in play? But what you saw today, it's a physical layer signal measurement.
Okay, great. I don't see any other questions coming up, so I'm going to actually ask one. Modulation complexity was mentioned, and Mark, you mentioned that some nonlinear approaches to modulation are with your QAM8 signal were there. But is modulation complexity going to be tied to the test equipment, or is there any software limitation there? That's a question for both of you, I guess. That because I did see we had some QAM16 in your demo, Sung-Hoon, and then in some of your other diagrams we had QAM64 type. But is there a tendency in the industry to go higher with modulation complexity or not?
Yeah, it's a good question. Sometimes people remind me that radio, wireless runs at 1024 and 2056 QAM. So what are you guys stuck at 16 for? I think the challenge is that the baud rate is so much higher that being able to maintain the type of linearity and dynamic range needed, even to go to 64 QAM at these baud rates, is proven to be quite difficult. So from a practical standpoint, and looking at interoperability, there's certainly proprietary solutions that can go to 32 and 64 QAM. But as a practical limitation, the industry seems to have settled on QPSK 8 QAM, 16 QAM. The nonlinear part refers more towards changing the distances between the constellation points, changing the power balance between the constellation points to reduce the sensitivity to impairments. Right? I mean, in a lot of ways, this is trying to squeeze another dB, another 2 dB. So I think, Sung-Hoon, I don't want to comment on your software, but at the physical layer, it's very much a matter of the same thing, having enough dynamic range and sensitivity to be able to see the signal and properly interpret it.
Yes. So, for the OMA measurement itself, it really depends on the hardware capability, dynamic range, and the amount of noise present. But of course, we need to consider that the more complex the signal you use, the shorter the reach. So you need to weigh out the benefits, looking at the noise budget, and and see what makes more sense in a practical sense. And comparing it to the RF microwave world, so they benefit from very pure crystal oscillators that optics don't have. I mean, optical laser is intrinsically noisy, a lot noisier than crystal oscillators. So
the phase noise is going to affect it a lot. Okay.
Yeah.
That makes sense.
Yeah. I mean, we make external cavity lasers that, from a commercial tunable laser standpoint, have the narrowest line width on the market. But we also see even with that, we see the impact. These are 50 to 100 kilohertz line widths. I would imagine the crystal oscillators are tens of hertz. So yeah, very, very, very different.
I think that's the end of our Q&A questions that have come up, but that was all really good. Great questions. And I just wanted to point out that I have dropped the handouts that we have here for the presentation into the handouts section of the webinar. Or if you want to get back to us with an email, you can certainly do that. And I wanted to thank everybody for attending, and this was a great session. I actually learned a lot, so hopefully everyone else did too. Thank you, gentlemen, for the presentations. They were very excellent.
Thank you.
Thank you.
everyone who
And
attended.
thanks for everyone for joining the webinar, and have a good afternoon.
Thank you very much. Bye-bye.
All right,
Thanks.
bye-bye.
Bye.